Okay, so the title of today's talk is from verified compilation to Shor's algorithm, and it's joint work with a whole bunch of people, several of which are at the University of Maryland, but also Robert has moved on to the University of Chicago, and we have a collaborator at Columbia as well. Okay, so quantum programming is not easy, and the question is, am I sharing my slides properly? Yeah. Great. The question is, when you write your quantum program, how do you know that you've actually done it correctly? Now, in the classical domain, you would probably test your program, you would run it, maybe you would use an interactive debugger if it wasn't working properly. But you're going to immediately run into trouble in the quantum domain, because when you try to use that debugger to look at your internal state, measurement is going to collapse that state and remove any insight that you might have hoped to gain. You could try to simulate your quantum program so that you have direct access to the state, but that's going to become intractable if your program starts manipulating states that are too big. You might even struggle to know what correct actually is if you're using quantum programming to do discovery, to do physics modeling or something like this. Of course, in the near term, things are even worse. We don't have that many qubits, and the ones that we have are error prone, and actually using them is very expensive. So what can we do? Well, I would claim that programming languages technology and formal verification in particular can be of assistance. So formal verification is a powerful tool that is used for producing high assurance software. And the idea is that you can mathematically specify what your program is meant to do, and then prove that the actual implementation of that program meets its specification. And a famous result in this space is the CompCert compiler developed at INRIA. It's a C compiler that has been proved to always produce correct output, that the target program's semantics are always a match for the input source program's semantics. Now, formally verifying a quantum program would not require actually running that program. So those challenges I mentioned about noise or intractable simulation or debugging would disappear. You prove that your program does what it's supposed to. You don't need to test it. At the same time, you might also like to prove that your compiler does what it's supposed to. And having done so, you can be assured that starting from the program itself does what it's supposed to, continues to do what it's supposed to as it's translated all the way down the stack to the final result, so that any anomalies that you see are outside of that proved correct software stack. They're part of the hardware, they're part of the noise, or something like this. And the hope is that this will give you much greater confidence in your development process that what you're doing is giving you the answer that you intended. Okay, so what we want is a stack that looks something like this. Each of these check marks means formal verification. So for example, here at the top, it means we've formally verified that the source program satisfies the specification. And then each of the intermediate stages, by being proved correct, preserves the semantics that you established was correct right from the beginning. And that way we know that the hardware instructions that are being executed really do what we intended them to do. Now, the challenge here is that while formal verification is advancing, Matt just mentioned F-star, that's one technology that's getting a lot of traction right now. That technology has been developed for classical programs, and these are different than quantum programs in many ways. So quantum program states, as we know, are represented by matrices of complex numbers. That's the way we think about them mathematically. And programs involve probabilities, trigonometric functions, and these tend to be things that are not well explored in the classical domain. So what that means is that we need to develop new frameworks, libraries, new automated decision procedures and whatnot in order to make this vision of a verified compiler stack a reality. So we've been trying to do that for the last couple of years, and our two products in this direction are SQIR and VOQC. So VOQC is the verified optimizer for quantum circuits, which is built on top of SQIR, the small quantum intermediate representation. And you can see in the picture here, the way that our setup currently works is that we start with an unoptimized OpenQASM program, which we can translate very simply to a SQIR program. These two representations are very related. SQIR is then the program is optimized by the VOQC compiler, the circuit optimizer, and then that can get translated back to OpenQASM, which is actually executed. And what we've proved is that the VOQC optimizations preserve the semantics. So all those changes we made to that input program do in fact preserve its semantics. There's no bugs. And we also have proved that source programs that you may have written in SQIR do what they're supposed to. While we designed SQIR originally as an intermediate representation for a compiler, we realized because it was so close to OpenChasm that actually people are writing source programs in low-level languages like this. We could also specify what those programs should do, in this case, those programs written in SQIR, and prove they do what they're supposed to. So all of the code and artifacts that we've produced are available on our GitHub site. It's at this URL. And I just want to highlight Robert and Kesha here as being the moral and implementation leaders of this project. As I mentioned, Robert is now an assistant professor at Chicago. Kesha is going to be finishing up in the next year. And, they've been fantastic leaders of this project. And, I look for really exciting things from them in the years to come. Okay, so this is the outline for the rest of my talk. I'm going to start by talking about SQIR, the simple quantum intermediate representation, and show what it looks like and talk a little bit about proofs of source programs. And then I'll spend time talking about VOQC, the verified optimizer for quantum circuits. And then finally, I'll talk about our ongoing work in proving a correct implementation of Shor's algorithm end to end. Okay, so what is SQIR? SQIR is an intermediate representation. It is a simple language for expressing quantum circuits. So in many ways, it's just another way of expressing the same thing that OpenChasm can represent, but in a format that's amenable for proof. SQIR programs are embedded in Coq, a proof assistant, and they are assigned a denotational semantics of matrices of complex numbers. So you can just think of it as saying, when I have a SQIR program, what does it mean? Well, what it means is if it's a unitary SQIR program, that's the first flavor of SQIR that we have, its meaning is the unitary matrix of the computation itself. And if it includes measurement for a full SQIR program, its meaning is going to be a density matrix representing the mixed state that results upon executing that program. So either way, we can think of in our Coq program, we're writing a function that takes a SQIR program as an input and produces a denotational semantics, produces a matrix of complex numbers as its output, which represents the semantics of that program. So I'm going to spend most of my time talking about unitary SQIR. It's an extremely simple language. This is the BNF for the language. So basically, a unitary SQIR program is simply a sequence of gate applications, either 1 or 2 qubit gates. That's the GQ or GQ1, Q2 parts there. There's going to be a particular gate set for your SQIR program that you're interested in. So it's parameterized by that gate set. And the indices that your program is going to operate on are concrete numbers. So there will be a global register of qubits numbered 0 to D, the dimension of that register. And basically your program is just a sequence of gate applications to those particular qubits. So the way that this BNF is expressed in Coq's programming language is shown here. So a SQIR program that U is a UCOM, a unitary command. It's parameterized by a gate set G, and then by this global dimension. And it has 3 possibilities. One is the sequencing operator. So that's where we have 2 UCOMs that are sequenced together to produce a program. And then we have the UAP and UAP2 cases, which are given a single or double qubit gate and the index that that gate should operate on, that will give us a unitary program. So the denotation, the semantics of our unitary programs is again very simple. Basically, the semantics function are these angle brackets, the semantic brackets. And you can think of that as a function from the SQIR program on the left-hand side to matrices, in this case, unitary matrices on the right-hand side. So for sequencing, what we do is we compute the semantics for each of the 2 unitary subprograms individually, and then we apply matrix multiplication, just like you would expect to do. And then for individual or 2 qubit gate applications, we use this apply function to apply the gate to the qubit that's specified, and then basically pad it out with the identity matrix for every other location. This only applies if the gate application is well typed. For example, it's actually applying to a qubit that is within the global dimension. And for the 2 qubit case, that you're not applying the 2 qubit operation to the same qubit, that would violate the no cloning theorem. If it is not well typed, it maps to the 0 matrix. So just for fun, this is what that looks like in Coq. We define a function UC_eval, that's the bracket function. It's parameterized by D, the global dimension, and it takes a SQIR program as an argument and returns back a two-dimensional matrix. And you can see there are cases for each one. I'm just showing the sequence case here, that basically the semantics of the sequence of two unitary programs is just the multiplication of the semantics of each of those programs individually. And I'm just not showing all the code for UAP1 and UAP2. So just as an example, here is a small SQIR program. The SQIR program is on the bottom. It's a single qubit application of the Hadamard gate to qubit 0, followed by C0 on qubit 0 and 1, and then C0 on 1 and 2. And that's represented by that circuit that's there on the upper left now. So this is the way we would assign the semantics to that program. We would first consider the semantics of the single qubit application of H, and that's going to use the apply1 function as we saw. We'll take the unitary representation of H of that particular gate, and that's the familiar Hadamard unitary matrix. And then what we're going to do is the apply1 is going to pad this out, so we'll use the tensor product to pad out the application of Hadamard to first the 0 qubit and then the identity matrix to qubits 1 and 2. And then we'll get this 8x8 matrix. We would do something similar for C0 0 1 and C0 1 2. We'll apply the apply2 operation. I'm not going to show the details of that, but having generated the semantics of each of those individual gate applications, we apply matrix multiplication to get the 8x8 unitary matrix that represents the meaning of that entire program. Okay, so all of this should hopefully just look totally straightforward, and that's good. That means we believe that the SQIR program is doing what we expect. Okay, so just like other quantum programming languages, so for example, Quill and PyQuil, we can, or Quipper, for example, SQIR programs don't exist on their own. They exist embedded within a metaprogramming language, in this case, Coq's programming language, which is called Galena. Quill programs are embedded in Python programs. And we can think of this host programming language as a circuit building language. That is, we write functions in Coq, for example, to build SQIR programs. And those Coq functions can be parameterized by Coq data. And that allows us to build parameterized circuit families as Coq programs. So here, instead of just writing, one at a time, the 3-qubit, 4-qubit, 5-qubit GHZ preparation program, we can write one Coq metaprogram that's parameterized by the number of qubits we're interested in, n. And then this program says, well, if you want the 0-qubit GHZ preparation state, well, that's just the skip function. For the 1-qubit case, that's just the Hadamard function. And for the n-qubit more than one case, then that's just going to be C0 applied to all the subsequent qubits with Hadamard to the first one. And the nice thing is, now that we have specified this as a metaprogram, we can prove properties about those metaprograms. So in particular, we could prove that this metaprogram, GHZ, produces the GHZ state for the number of qubits that we specify. That is, we can prove that little GHZ n applied to the 0 state is going to produce the GHZ state of n qubits, which we can, again, define in Coq. So the mathematics of that description is on the left there, and the Coq definition is just to the right of it. It shows the way that you would specify the GHZ state itself. And the lemma at the bottom says that the semantics of little GHZ n, when applied to the 0 state, assuming n is greater than 0, will give us the GHZ state when we're finished. And then we can prove that in Coq. The way proofs go in Coq are you use a sequence of tactics. Those tactics can be provided by Coq itself. There's a bunch of decision procedures that Coq provides, for example, handling linear arithmetic. But you can write your own tactics, and we did that as well to improve the automation quality of your proofs. Either way, no matter what proof strategy you use, Coq confirms that your proof is correct. There's no possibility of you making a mistake in your proof. The proof assistant, with various caveats about the proof assistant, its logic itself being correct, is able to check that your proofs make sense no matter what automation you use. So SQIR was designed to work well in this regime. There's no magic here about doing proofs. They're just like writing software is not easy. Writing proofs is not easy either. And good software engineering design makes writing programs easier and better. And likewise, good proof engineering design is needed to ensure that your system works well. So SQIR was designed after many false starts to enable proof in Coq in particular. So one design choice that we made that turned out to be really important was that qubits are referenced using concrete indices, right? We say that you're applying the C0 gate to qubits 0 and 7, not to some abstract qubits X and Y. And the reason that that's useful is that it makes the semantics easy to express. You just map directly to the matrix using padding the way that I was showing you. If I didn't know what X and Y were, which qubits they identified, there would be no easy way of me to mapping the semantics of C0 to a particular matrix. There's like a whole family of matrix that it could apply to, which would make proofs of equivalence very difficult. Another nice feature is that especially when performing optimizations of program transformations, disjointness is a syntactic property. As long as those two arguments to C0 are different, I know that they reference different qubits, or that would not be true for X and Y, which could, for example, be mapped later to the same qubit. Separating the unitary core from the full language also turned out to be really important. The unitary matrix semantics is much simpler to work with than the density matrix formulation. And since many times we only care about the unitary matrix all the way up to measurement at the very end, keeping these things separate simplifies the proof process. And this is just an example of the benefit of doing our work in Coq itself. We're able to use many of the different Coq libraries and tactics to approach proofs in a different way. So for example, for some of the more sophisticated source program proofs that we did proofs according to consideration of distinct basis states. The alternative might have been to take the program and map it to some massive matrix and then try to reason directly about the matrix. But we didn't need to do that. We could reason about basis states instead by building a library on top of that matrix semantics and doing proof by rewriting. We can build other semantic approaches on top of this as well. So we have a path sum semantics that we've developed also. And we can also develop new automation, which we have done, for example, in proving matrix equivalence is correct. So I think all of these features, maybe this last point is maybe a distinguishing characteristic of SQIR and our infrastructure, just simply that it has a bunch of flexibility by virtue of being built in Coq that's allowed us to extend it and scale it up over time. So at this point, we have a paper actually coming up in a couple of weeks at the Interactive Theorem Proving Conference that describes all of our source program proofs. So that paper is on my webpage. And it talks about proofs for all of these different quantum programs. The most interesting ones are Grover's search algorithm and quantum phase estimation, which is a key part of the order finding algorithm in Shor's algorithm, which I'll mention a little bit later on. And all of this stuff amounts to about 3,900 lines of Coq code and 3,500 lines of the actual proofs. Okay, so now I'm going to talk about VOQC, our optimizer for quantum circuits. So as I mentioned, the way the general setup works is an OpenQASM program can be translated to a SQIR circuit. Maybe then you prove something correct about that circuit, and then you transform it by optimizing it. And this optimization might be translating the circuit to use a particular gate set, optimizing it according to that gate set, and then perhaps mapping it to the architecture to make sure that it satisfies architectural constraints. Maybe not all qubits can be, say, connected via CNOTs, and so you have to transform your program so that this particular architecture's constraints are satisfied. And the fact that we have proved all of these transformations correct means that we know that the input and output SQIR circuits produce the same states. They are equivalent. Mathematically speaking, this first bullet indicates what I just said. It says that we want to prove that for any transformation of a SQIR program, that the semantics of that program is the same before and after the transformation. So we write that as to say T, the transformation applied to the program P is equivalent to the equivalence symbol there, the original program P. And most of the time, proofs proceed by induction on P, where P is, in SQIR, basically that sequence, that list of gate applications. So here's an example optimization that we've defined in VOQC. It's not propagation. And basically the way that it works is it starts with a not gate, X, and it moves it to the right inside of a circuit, trying to get it next to another X gate. Once it does, it can eliminate that pair of X gates. What we see here is that the definition of the code at the bottom, and you can see the example is exercising different parts of the code. So in the first case, we move X on the other side of the C0. That's allowed because the qubit that the X is operating on is the same as the target of the C0, so you can just move it right to the other side. When we move the gate to the other side of the RZ gate, this is a Z rotation. What we do is we negate, we take the complex conjugate of that gate, which just causes us to negate the angle for the Z rotation. And then finally, we have the two X's next to each other, which in this case is going to allow us to kill those two gates. So we want to prove that for any instruction list, propagate X has the same denotation as the original instruction list with an X tacked on the front. That the idea is if we see that latter thing, X followed by a list, we would like to call propagate X on it with the potential, hopefully, of eliminating that X. And so the thing we want to prove is that propagate X list is equivalent to X followed by the list. And so we can do that by induction. So in the first case here, if we get all the way to the end of the list, then that means that we have to output X. We were unfortunately unable to remove that X. And you can see that this is just a base case of the proof that propagate X on the empty list returns X just itself, which is equivalent to X followed by the empty list, the right-hand side of the equivalence we're trying to prove. For the second case, this is eliminating the X where the two X's cancel each other out. This works because in canceling them out, T, the list that's left, is equivalent to XQ followed by T. And we can prove that according to the equivalence that XQ is equal to the identity matrix. And I'll mention that a little bit more on the next slide. And then finally, for this, this case here, the bottom case, this is just showing that, again, applying inductive reasoning. In this case, we can apply the inductive hypothesis to propagate XQT, and then do a little bit of algebraic reasoning to get the result that we want. So that's an example of a p-pole optimization. It just moves things around until two gates are next to each other and then cancels them out. A more interesting optimization is rotation merging, and this allows us to find and merge multiple Z rotation gates that are not necessarily next to each other. So basically what we do is we identify groups of gates that could be potentially combined, and we realize that these gates can be moved around and their angles can be combined in that movement process. So we can reduce the number of gates by adjusting the angle of the one gate that's left. So just for time, I'm not going to spend a lot of time explaining this. Basically what happens is there's a process by which each of the abstract states of the qubits is maintained as we move sort of through the circuit. And we realize when we get to this RZW that essentially the B that we had on entry to RZX is the same B modulo the rotation that we're getting at the beginning of RZW, which then allows us to merge those two rotation angles, X and W, there at the right-hand side. So this is based on an optimization that was not ours. It was proposed by Nam et al. In an earlier paper. And the novelty here is that we've actually proved in a verification framework that this optimization works. So you saw in that not propagation proof that we needed to use this equivalence that not gates cancel out, that they're equivalent to the identity matrix. And there's actually a bunch of other equivalences we needed to prove as well for each of those reasoning steps. We prove these as lemmas, and we have a Coq tactic that we use to convert matrix expressions to what we call grid normal form that allows other automation tactics to pretty much automate the process of proving these equivalences. So a lot of our proofs are basically structural by induction, and we apply decision procedures based on that use these equivalences as subroutines. So there are many other optimizations that I'm not going to talk about. The last thing I'm going to mention is circuit mapping. So this is where you have a program that uses qubits that the architecture is not able to support. So what this shows is I have a CNOT program that operates on qubits 0 and 2, but I have architecture specification that only 0 and 1 or 1 and 2 can operate together. There is no way that 0 and 2 can be fed in to a CNOT gate. So that requires us to transform our program to swap the states on qubits 0 and 1 so that we can perform the CNOT. And then what we do is we prove that this mapping is equivalent to the original up to a permutation. And that permutation indicates how the logical qubits have been moved around. So we've implemented a large number of optimizations. They're shown there on the right. Most of them were inspired by or came directly from the Nam et al. Paper. However, some also came from Qiskit-Terra and TCAT, and we applied that series of optimizations to a benchmark and compared it to the performance of other optimizing compilers listed there in the lower left. So the benchmark was developed by Amy et al. It's a bunch of programs that involve arithmetic circuits that you might see in oracles for quantum programs, but also quantum gates as well for quantum aspects of those algorithms. And the benchmarks ranged in size from a small number to many gates and a small number to many more qubits. And we measured effectiveness in terms of gate reductions and also the time taken to perform optimization. So this is just showing the total counts. I'm going to summarize all of these results in just a moment. The numbers in pink are interesting because these are bugs that other people found in the original implementations of these optimizations. So some were in Amy et al.'s compiler, some were in the original Nam compiler. We didn't find these bugs, other people found them, but this is just to illustrate that having a proved correct optimization can be useful because it might be difficult to detect otherwise. So this is the summary of the results. VOQC was able to reduce total gate count by just about almost 19%. So it's only bettered by Nam et al. And that's the reason is obvious. We didn't actually implement all of their optimizations. We implemented a subset. On T-gate count, we're close to, we're also very close to the top. PISX, which was designed to reduce T-gate count, is the very best in this particular case. And then in terms of compilation times, VOQC is pretty competitive. A bunch of these compilers are written in Python, so it's no surprise that they're a little bit slow. The Nam et al. Compiler is written in Fortran, so no surprise that it's kind of fast. Okay, so this is VOQC in sum. A bunch of optimizations of a different styles and a big pile of code. Later today, Kesha is going to talk about improvements we've made to VOQC since our POPL paper, including a Python front end and a bunch of new optimizations and such. So check that out at the end of the day today. Okay, so in the last few minutes, I'm going to talk a bit about our work on Shor's algorithm. So this is a depiction of Shor's algorithm. Shor's algorithm is a hybrid algorithm in that it has classical pre and post-processing parts with a quantum core. So here on the top part of the picture, the first part of Shor's algorithm does a bunch of classically efficient steps to see whether or not the number n that you care about has a non-trivial factor. If it can answer the question before doing anything quantum, it does that. If it can't, it then performs quantum phase estimation on a in-place modular multiplier. And that's a substantial quantum program. At the very end of that, it then checks to see whether the result, which is probabilistic, came out the way that we wanted to. If it didn't, it needs to rerun. And there's a guaranteed success probability that you only need to rerun so many times. And even when you do rerun that few number of times, you're going to do a whole lot better than the classical algorithm that would have taken to factor that input. Okay, so the features of this algorithm are classical pre and post processing with a quantum core, the use of a large arithmetic circuit, this in-place modular multiplier connected to quantum phase estimation, and then also, a pretty sophisticated mathematical proof that this is doing what we want. Not only that it's giving you the right answer, but it's doing it in a highly efficient way. And so far, our work is not completed here. It's about 10,000 lines of code in total, combining both the specification of the algorithm and these proofs. Okay, so what were the challenges given what I've already told you about to getting this far? Well, the first part was that order finding is, as I mentioned, connecting quantum phase estimation, not a very big program, but an interesting one, to a very large but not very interesting program, this in-place modular multiplier. And getting this ladder multiplier to work and being confident that it was correct was quite a challenge. We ended up developing a new language, the reversible computation intermediate representation, for writing this arithmetic circuit and establishing that it was actually correct, and then proving that compilation from RCIR to SQIR was also correct. So with that, we were able to connect it to QPA to get us the full quantum circuit that we could believe in. Another challenge was that Shor's algorithm has classical and pre and post processing components. So, what we wanted to do was to have a program that we could say, from the command line a.out, run this program, which meant we need to implement the classical parts. We needed to implement them in a way we could prove that they were correct when combined with the semantics of the quantum part, and do that whole process end to end. And so that prompted us to develop a framework for hybrid classical quantum programs and reasoning about their interaction. And then finally, it was quite non-trivial, as I mentioned, to prove the correctness and efficiency of this algorithm. We ended up having to prove some number theoretic results that had never been proved in Coq before, and contributed to the mathematics library in Coq for that. So we are able to run our version of Shor's algorithm. I don't have time to explain this slide, unfortunately, but basically we were able to connect it up to a simulator, the DD-Sim simulator, which actually will be discussed later today. And we were able to show that our verified bounds are consistent with what we observed empirically when running for numbers n up to 200. Okay, so I'm going to finish up so we have time for a few questions. I've told you about SQIR and VOQC, two building blocks of the verified quantum software stack that we envision. This is powerful enough to verify state-of-the-art optimizations and source programs. And it's resulted in novel frameworks, libraries, and automation. And we're working on a bunch of things now. New optimizations. We're trying to get our stuff integrated into the Arlene benchmark suite. Kesha may have something to say about that later. We're developing new proofs. Shor's algorithm is one. And then finally, we're developing new verified elements of the quantum stack. So right now we're developing a new source programming language for compiling efficient quantum oracles. And we hope to have a draft of that work to release in a few weeks. Okay, and I'll leave you with this resource slide that talks more about what you can find if you go to our website to look at the code that's there. Thanks for your attention.